Okay, basically I'm going to run through mitochondrial DNA and genetics as fast as I can here in less than 5 minutes. So here's what we got. Mitochondrial DNA is maternally inherited exclusively. It's never paternally inherited. It occurs in 100% of siblings. All of the offspring of the mother are affected. So every single one of the mother's children is affected. If you're infected, the father will not pass it on at all to 100% of their offspring. The mother will pass it off to 100% of their offspring. Let's consider the mitochondrial population in a cell. Homoplasmy is whenever all of the mitochondrial DNA is either mutated or all of it is not mutated. It's all the same. Heteroplasmy is whenever there's a combination of mutation and non-mutation. Replicative segregation I kind of saved because it deals with the bottleneck effect. And what this says is whenever you have a cell with mutated mitochondrial DNA and it replicates, some of the offspring will have mutated mitochondrial DNA and some will not have mitochondrial DNA. And that's because of the bottleneck effect. There's only a certain amount of mitochondrial DNA that's passed on to each progeny cell. And so, like here you have 100, only 30 is passed on to each progeny cell whenever they mature to get back to 100. Then they're going to duplicate the mitochondria that they've been given. So look at this figure here. If you have more mutated mitochondrial DNA, then it's going to produce a cell that duplicates more mutation, and it's going to overall have more mutation, 80% mutation coming from 20%. That's the concept of bottleneck effect and what causes replicative segregation. You have two pathological findings with mitochondrial disease. One's ragged red fibers. Histologically, you're going to stain the mitochondria with Gomori trichrome. It'll stain red, and you'll see abnormal cristae patterns. Ragged red fibers, you're going to see that again in MRF. Cytochrome C oxidase deficiency, what you're going to get here is this is caused by rRNA or tRNA defect, and it's going to deal with complex 2 of the electron transport chain. Okay, moving on to these classic syndromes. We need to know 4 of these. LHON is Leber hereditary optic neuropathy. And what you need to know about that is that the onset is young adults. It deals with an NADH dehydrogenase point mutation that affects complex 1 of the electron transport chain. If you consider neurogenic weakness, ataxia, and retinitis pigmentosa, NARP, you have a mitochondrial DNA ATP subunit 6 mutation, and subunit 6 is going to affect complex 5. Look at MELAS, which is mitochondrial myopathy, encephalopathy, lactic acid, and stroke. You have a heteroplasmic point mutation, A to G point mutation, caused by tRNA leucine mutation, and that is going to affect complex 4. Lastly, we have myoclonic epilepsy with ragged red fibers. Going back to the ragged red fibers here, this is due to a tRNA lysine gene mutation. Onset is childhood through adulthood, and the tRNA is again complex 4. So just reviewing the electron transport chain, you have NADH dehydrogenase that affects complex 1, cytochrome C that affects complex 2, cytochrome B that affects complex 3, tRNA and rRNA affects the COX here, and that affects complex 4. And lastly, the ATPase 6 or the subunit 6 here, mutations will affect complex 5. Lastly, just want to talk about age a little bit. Mitochondrial DNA mutations occur more with age, and it gets more severe with age. You have no antioxidants or limited antioxidants, then you have more reactive oxygen species. That'll encourage mitochondrial DNA damage, and that'll cause electron transport chain damage, and that'll cause additional mitochondrial DNA mutations, will eventually cause more and more cell apoptosis. Thanks.